So I'll be talking about this project we have called HodgeNet for graph neural networks in the edge space. I'm Mitch Roddenberry. I'm an EC at Rice, and this is work with my advisor, Santiago Segarra. Okay, so a lot of this graph machine learning stuff has its basis in these ideas of signal processing and machine learning for network data. And core to this is the idea of generalizing these well-known Fourier bases to non-Euclidean domains, right? So up here at the upper left, you can kind of see these normal Fourier basis type functions. So you have a smooth DC function at the top, this straight line, and then these sinusoids that represent frequency, right? And in these more irregular domains, you get smooth signals in the sense of variation, right? So a smooth signal is locally uniform, and a high frequency signal has a lot of variation locally, right? So for example, the slower signal on a graph, these smooth ones on the left are all the same basically, and then the high frequency ones on the right have a lot of variation locally. So using these ideas, you can generalize a lot of common signal processing ideas to think about filtering, so you can perform tasks such as smoothing or interpolation or compression. And then when you mix in some nonlinearities and coarsening, you can get graph convolutional networks, as was talked about earlier. Okay, so this is all concerned with node data, right, in this general graph signal processing framework. But some data that we're interested in might be modeled best as a flow over the edges of a graph, right? So some examples could be urban traffic flow over roads, migration patterns between countries, or like a supply chain in a business setting. And so our main question is how can we apply these signal processing and machine learning methods to flow data to perform tasks such as interpolating flows or localizing sources in some system? Okay, so one tempting option might be to form what we call the line graph. And essentially what you do is you take your original graph and map it to a node in a new graph. And then you connect nodes in your new graph based on the way the edges in the original graph touch each other, right? So you can see node edge E in this original graph on the left becomes node E in the line graph on the right. And then edge E and edge B touch at node 2. Thus you connect node E and node B. Right? And then your flow signal from the edge would just become a node signal in your new graph. So this is bad, is what we like to claim. And the reason for this is in graph signal processing and signal processing in general, we're generally leveraging some assumption of smoothness over our data. It kind of makes sense. And using this construction, smooth means locally uniform, right? And this doesn't match what we would like about flows. So here's an example. Imagine this is a drawing of a road, right? Some intersection between roads. You have a major artery kind of going along the top here, and then a small road branching off on the bottom. A uniform type of smoothness assumes, okay, the traffic flow over all of these branches is going to be about the same. But if you think about a small county road branching off of an interstate, that doesn't make any sense, right? You're going to accept the interstate to have large volume and the county road to have a small volume. What we would prefer is for smoothness to mean conservatism, right? So all of the flow going into some kind of junction leaves the junction, right? And so we claim that flows are generally conservative and not uniform. So keeping this in mind, we propose a new operator, which is called the Hodge Laplacian, right? Now what the Hodge Laplacian does is it encodes relative orientation of flow, because this is a very directed type of phenomenon. And then it captures these properties of conservatism or gradientness, right? So a gradient flow is characterized by sources and sinks, where flow goes from a source to a sink, right? And then these conservative flows, which are captured by harmonic and curly flows, basically are characterized by cycles, which is what we talked about earlier. And so in the Hodge Laplacian, the null space of this operator, which is smooth, is conservative, and the image, or the non-smooth part, is gradient. Okay, so now with this tool we can talk about a couple problems to solve. The first one we consider is that of source localization. And so in source localization, we model a flow as being induced by some smoothly varying set of sources and sinks, right? And so we get to observe a flow and we want to figure out where it's coming from, right? And so we use a neural architecture called an aggregation graph neural network to accomplish this. Okay, so based on this paper and this unrendered image, yeah, we take a flow on a graph and aggregate information at a single edge. So you pick an edge and try to aggregate information locally via multiple steps. And this forms a regularized time domain signal, which we can then classify using a traditional convolutional neural network, right? And so our experiment, we create synthetic graphs with ground truth communities, and then basically create flow signals that originate at one of these communities and then add noise to make things more realistic. And then we train an aggregation graph neural network to recover which community the flow originated from. So this is a classification problem. And we can use all sorts of different operators, like the adjacency matrix was mentioned earlier, to capture this local information. And we show that our proposed Hodge Laplacian, which is what we want, converges to have a high classification accuracy a lot faster and just performs better in general compared to using this proposed line graph operator or thinking about things in the node space using some inverse transformations. Okay. So the next problem we consider is that of flow interpolation, right? So if you consider an urban traffic network, let's say you want to measure how many cars are going across every road in a network, but that's very expensive and infeasible. So you want to just measure a few roads and infer the flow everywhere else, right? So you see in our example on the left, let's say these black edges, you actually observe, right? You know the flow over them. And you want to infer the flow over these red edges here. Okay. So the data set we consider is the traffic flow data set in Anaheim, California. Okay. And for this, we use a recurrent neural network type architecture, where we basically apply our operator to our flow signal repeatedly to get another sequence. And then using these shared weights combined with nonlinearities, after however many steps, we can form a prediction of a flow at an unknown edge. And as you can see in this table down here, the Hodge Laplacian outperforms other methods such as the line graph or using a random architecture or no architecture for baseline comparisons for interpolating 10% of the edges in the Anaheim flow network. Okay. So overall, our main claim is that line graphs are not enough for tackling problems related to flows on graphs because the notion of smoothness is inappropriate. And to do better, we can use things like the Hodge Laplacian that suit our intuitions about this type of data better. And with that, I thank you for having me.
Yeah, we have plenty of time for questions.
Do you have to apply the same operator everywhere in the network?
I mean, that's generally what we do. It'd be kind of interesting to think about varying it over the network, right? You can do different regularizations based on local properties of nodes or edges or something like this. Yes.
Thank you.
Or if not, let's find a speaker again.